Okay. Good afternoon to all. My name is Francesco Bucci. I work at the Institute for Hydrological Protection of Central Italy, based in Perugia. And I will talk about an episode of drainage reversal revealed by geomorphometric analysis of fluvial terraces. Our case studies, sorry, but I have problem with, okay. Our case study is in Central Umbria, but episodes of fluvial reversal have been described elsewhere. Here I show just two representative cases from literature, just to introduce that a reversal of a river can occur at very different scale, in different geographic context, and in response to different processes, continental topographic changing driven by continental tectonics, in the example from China, or simply local rock strength variation across cliffs, in the example from Israel. Whatever the reason, river reversal processes response to one or more changing at the Earth's surface. So studying the reversal of a river represents an interesting way to investigate the nature of this changing. We explore these topics in central Italy, along the basin of the Puglia River, a tributary of the Tiber River. The area is not far from Perugia and not far from the epicentral area of central Italy earthquake of 5 years ago. The effects of quaternary faulting are clear in the study area, where the Puglia River flow through a ridge crossed by quaternary faults. And the river course can be divided in three main parts. Upper and lower course drain gentle landscape, modeled on soft sediments of quaternary age, while the medium part of the course flow in a narrow valley, modeled on more strong rocks of the bedrock, mainly flysch deposits of Miocene age. The investigation of the area, including portion of the Foligno Valley and the Tiber Valley, was based on a photogeological survey using black and white stereoscopic air photograph at 1 to 33,000 scale, and a multi-scale air photo interpretation using more detailed photographs in color at 1 to 13,000 scale was focused along the middle course of the river, which is our target, because here several order of fluvial terraces crops out. For the same region, field check also was performed along the medium course of the Puglia River, where a total of 84 survey points were collected in order to integrate and check the photo-interpreted information. And overall, we checked and formalized several thematisms, including 6 order of fluvial terraces, landslides, faults, bedding traces, alluvial fens, alluvial deposits, and were preserved outcrops of terrace deposits were surveyed and characterized. Among the other thematism, we selected traces of the fluvial terraces and computed their surface attitude following a procedure based on a GrassGIS tool, GeobedPy. The GeobedPy tool in origin was developed to reconstruct the attitude of bedding planes and requires a bedding traces map and a dam. And in this contribution, a map of outer and inner edges of fluvial terraces were used in the place of the bedding trace map. The procedure based on a script that iterates 5 steps. First of all, trace of terraces age is drawn on a base map, and nodes of the red line are joined with a single segment, blue line, to form a polygon. Equally spaced points are selected along the boundary of the polygon, and their elevation is obtained from the dam. In this case, we use TIN Italy as a dam of 10 meters of resolution. Elevation values along the trace of terrace ages are interpolated to obtain a 3D model of the terrace surface plane. And finally, the mean values of slope deep angle, and aspect deep direction of the terrace surface are then estimated. More about the GeoBed PY, the script can be found here in this publication if you are interested. At the end, the script returns a point vector map containing information of deep angle and deep direction of every terraced surfaces. Okay, at this point, terrace attitude data were separated and grouped by order, and they are displayed as simple arrows pointing toward the deep direction and plotted on an elevation map with outlined for each order the range of elevation. So this is the case for the first order of terraces. And these are the resulting map for all the order of the terraces. To compare the map together, for each order, the deep direction of the terraces were analyzed in Ross diagram to display the statistical distribution of the directional data, and also flow direction of the present day drainage network was also computed in the Ross diagram for comparison. If you look at the first three maps, the deep direction of the terraces 1, 2, and 3 of the order 1, 2, and 3 display three quite constant maxima, and indicated by the yellow arrows. Terraces dipping toward the southeast are interpreted as related to an ancient southeast direct river. And terraces dipping toward the south, southwest, and the northeast are interpreted as related to the left and right tributary of this ancient river. The same can be observed for the order 2 and 3, 2. Deep direction of the order 4 still show evidences for a southeast direct ancient river and southwest direct tributaries, while terraces dipping toward west and southwest are interpreted as related to a new west-southwest draining river. So the two rivers are separated by an area without terraces, which is interpreted as a transient divide between two divergent rivers. Deep direction of the terraces 5 and 6 together are interpreted as related to the lateral stream contribution to the terraces building, and because they are very similar to the distribution of the flow direction of the present day tributaries of the Puglia River, and northwest and west direct maxima in the last Ross diagram record the present day flow direction of the medium and the lower course of the Puglia River. If you look at the medium course, the modern flow direction is exactly opposed to the deep direction of the terraces for the order 1, 2, 3, and 4, related to the ancient river that we call the ancient Puglia River due to the position close to the modern Puglia River course. So we interpret the evidence as the result of a 5 kilometer long inversion of the medium course of the Puglia River. So ancient Puglia River flows toward the southeast, and modern Puglia River flows toward the northwest along the medium course. The rain profiles crossing terraces of each order, of the same order, were used to test and support our interpretation. Profile 1, 2, and 3 show well the southeast dipping paleoprofile of the ancient Puglia River. The profile 4 and supports the interpretation of a divide between two opposite rivers, while profile 5 and 6 are consistent with the modern Puglia River profile. So overall, terrain profiles show a progressive cannibalization of the ancient Puglia River course, operated by a younger west draining river aggressor. Field survey also confirm our interpretation In particular, directional data of pebble imbrication from terraces of the order 4 and 5 confirmed the river inversion. Looking at the stereo plot, red arrow is related to pebble imbrication in deposits of the order 5 and indicate a north-northwest flow direction, which is consistent with the reversed Puglia River course that flow toward the northwest. Blue arrow is related to the order 4 and indicates a southeast flow direction, which is consistent with the Paleo River course, which is with flow toward the southeast. And finally, pink arrow is related to the order 4 and indicate a southwest flow direction, which is consistent with the lateral stream contribution to the terrace building. Results are synthesized in a 3-stage model of time-space reversal of the Puglia River and contextualized in an evolution model of the Central Umbria. According to the model, active faulting in the Puglia Valley during the early Middle Pleistocene forced the river to flow parallel to the active fault in southeast direction toward the active subsiding Bastardo basins. And during the mid-late Pleistocene, active faulting and subsidence progressively shifted toward the east, toward the Foligno Valley, while the upper course of the ancient Puglia River was progressively captured toward the west. And from the late Pleistocene onward, active faulting and subsidence definitively focused to the east in the Foligno Valley, while the Puglia River experienced the diffuse uplift and erosion of the deposits here. And Puglia River definitively shifted and reversed its course, and its direction was no longer actively controlled by the fault's geometry, no more active. So the main implication of our finding is that the inversion of the Puglia River was driven by the evolution of the active tectonics in the study area. As a consequence, more in general, fluvial reversal episodes could be used as geomorphologic indicator of changing in rate and locus of tectonic deformation, with benefit for studies of active tectonics and models of landscape evolution under variable tectonic forcing. About methods of attitude computation, it was set up for bedding trace analysis, but it works well for terrace age analysis too. So our results open the possibility to apply the methods to other mapped traces with a geomorphological significance as planation surfaces or abandoned valley, paleo shoreline, and so on. For the future, we plan to date the river terraces to better determine the timing of inversion of the Puglia River to constrain the space-time changes of fault activity. And of course, we also plan to investigate other river inversion to test the general workflow and to extend the application to other environments. Thank you very much for listening.